So this is the architecture, this is the output stage of the DAC that we implemented. This is the main cell here, the DA switching output cell. This is the current source, and then in its drain a calibrating DAC is connected. So this calibrating DAC can generate correction current, either add or subtract correction current, so that I unary is actually adjustable. This is a current cascade, and at this point the current either goes to the DA switches for a normal DA conversion, or we can activate this, so we switch off this branch here, and the current is redirected through this probe transistor into the current comparator. And as you can see that the current comparator here subtracts a reference current, and then the difference between this current and the reference goes to a current sign detector, which can detect 1 bit information, can give us 1 bit information, either current flows in or flows out, the difference current. And then this is read by the algorithm, and then the calibration DAC word is updated according to the algorithm that I just discussed in the previous slide. And this is the output cascade. So you see that all these transistors are actually thick oxide transistors. This is the requirement for the integration of the DAC unit inside the I/O bank. Other things which are interesting for this architecture, so the main novelty here is that we have one stage, one phase in the calibration algorithm for which we first calibrate for the gain mismatch of the DAC cell. In this way we relax the requirements for the full scale range of the calibrating DACs per current source. So we have multiple parallel D2A converters, and the first thing that we do is that we will calibrate the gain error. And as the gain error, so if they are mismatched, we will calibrate first the gain errors, and as the gain errors are minimized, or the full scale ranges of all DACs are the same, then we will calibrate the mismatch errors, so that we can utilize in a more efficient way the full scale range of the calibrating DACs which are embedded inside the DA cell. So this is one cell, and we have many of these in parallel, and in the output we sum up the current contributions. Another interesting thing about our architecture is using local cascade for biasing. This is the local cascade, so every cascade here is individually biased. So we generate at one place in the chip the biasing currents, and then locally, only locally, we translated this into a bias voltage for the current cascades. And we do this to isolate the different cells that we have here from seeing each other. So if you have a switching in one cell, it will not propagate this switching to the other cells through the biasing network of the cascades. Because why? Because the cascades are locally biased. Then we have these bleeding currents. Here are the bleeding currents, and the main purpose of the bleeding currents is to linearize the output cascades, so that these output cascades remain in saturation for different values here for different digital information, switching M3 and M3 plus and M3 minus. These bleeding currents will always keep M4 plus and minus turned on and in saturation. Then the total output current is 20 milliamperes, which is terminated on a 50 ohm differential load. So this is the output cell. Then we have the digital train, starting from a digital bit, which is in digital domain, single-ended, our first task is to translate this into a differential signal, and we do this in inside the master-slave latch, synchronization latch, and we split it here, and then we align with the clock. All this is in tin oxide so that the timing is very accurate. And after that, this information, this 1-bit signal, needs to be translated into the high voltage 2.5 for the thick oxide transistors. To do this, we use a level shifter. So these levels, plus minus 0.1 volt, will be translated to 2.5 volts and then half range. And then this is fed to a CML driver, which will adjust the levels of the signal to be good for the current switches in the DA cell. So all these transistors are thick oxide and these are thin oxide. Then this is the floor plan of the whole DAC cell. Here it is the digital part. Up to here we have the thin oxide digital transistors at 1 volt, and we have a very good isolation between the analog part and the digital part. So here the switching is very active, CMOS switching, generating a lot of disturbance, while here in the analog part we keep everything quiet and clean. For digital gates we use CML logic, for which only constant current is consumed, and we don't have switching of currents in the power supply. The synchronization, the timing synchronization, is done in digital domain thin oxide transistors, low voltage, so that it is very accurate. We have smaller, lower parasitics in thin oxide transistors, and we can have very accurate timing. Now, yeah, I already said noisy CMOS logic is isolated. Look at the whole DAC area. It's just 0.037 square millimeters, and here the areas of each block are given. Another particular thing that you should pay attention is the area of the array of current sources. It's only 0.0076 square millimeters, and this is because we use calibration. So the current sources are designed with smaller area, and of course if they are small in area, their mismatches will be large, but we can calibrate their mismatches. That's the trick. So you see that the calibration, okay, we add a little bit of calibrating like this block, but still this allows us to design a very small area array of current sources. And you can see here the areas of the current sources actually are given. If you compare this with other papers, you'll see that here we gain a lot of area by allowing small arrays of current sources.